Bling. Oh, where'd my pen go? What?
I'm not. She's a color out, but she basically ruins the point of an eraser. But then it's too big. It's down here. No. Look. Yeah, but you can erase. I have a couple on the page.
Yeah, no, I believe that. Sandpaper it or something.
Okay, we all need to speed up a little because Karen is in my back.
Karen. Okay.
Yep.
So, when we, in Algebra 2 and the beginning of this year, we talked about scatter plots and linear regressions, yeah?
Oh, we're doing stats.
I know.
We're so golden. We're so golden.
Okay, so let's suppose you have a scatter plot that looks a little something like that. Okay? Could I find the equation of a line that fits that data pretty well? Absolutely. Okay? Now,
Are you talking about
find the equation of a line that fits the data.
Yeah, but is it using the point or just using the graph?
Using the point. Now, listen. Let's suppose we are biologists and we have some bacteria cultures and we're measuring them every so often. And we graph a scatter plot of what we notice. And when we graph that scatter plot, we get a graph that looks like that, which is what you would expect with a bacteria growth. How can I actually find the equation of the exponential function that fits that data as best as possible?
Well, you either use your calculator by putting the points in, or to log the y coordinates and make it linear.
Very nice. So, every single one of these points is an xy coordinate, right? Where the x coordinate is independent, so we'll call it x. But the y coordinate is some exponential expression like that, right? It's some exponential. And it's an exponential that depends on whatever the input x is. Well, what we can do is we can transform this set of data. Let's take all of these xy coordinates, leave the x coordinate alone, but let's take the log of the y coordinate. Because what happens when you take a log of an exponential? It turns linear, right? No matter how much that exponential has been stretched, shifted, and reflected, it'll turn linear. Let me prove that to you. If I take a times e to the bx minus c plus d, all exponential functions look like that, agreed?
Yes.
Every single exponential function in the world looks like that. So you're telling me if I take the natural log of this, I'll end up with a linear. Or not, let's say common log. Because I want the bases to be different, because I don't want them to cancel. Make it as hard as possible. Right? Well, there's a problem with that. This plus d. Right? So I'm thinking maybe this wouldn't work if it was a exponential set of data that's been shifted up. Oh, but that doesn't matter. You still got that plus in the parentheses. So I'm thinking if you're a statistician and you want to fit an exponential to a set of data, you've got to first shift that data down, then take the log, and that'll linearize it. But I don't know. Linearize it. But anyway, let's ignore that vertical shift. Will this turn into a linear? Well, we have a rule that lets me do log A plus log E to the bx minus c, and then that becomes log A plus bx minus c times the log of e. That is a linear expression, where whatever b log e is, that's your slope, and then whatever log a minus bc log e is, that's your y-intercept. Crazy, right? But that is linear, for sure. You've got a variable multiplied by some nasty number, and then another nasty number added to it. So if your y-coordinates are exponential, taking the log of them will make them linear. Then I can just fit a line to that linear set of data. Then hopefully we can figure out how to take that line and convert it back to the exponential that we really had to begin with. Does that process make sense? Okay. I don't like the example your book starts with. What's this? I didn't even look at this. What's this? Oh, exponential growth versus exponential decay. There's something called a Gaussian model. It's like a bell curve. There's a logistics model, which is very important in some real-life mathematics. Bacteria grows like that. Natural log, common log, whatever. Next. This is a cool problem. Maybe we'll get back to it. I want to make one up instead. Let's take this set of data. How about this data 0, 0, 1, 3, 2, 5, 3, 10, 4, 19, 5, 38, 6, 70. Okay? Let's look at that set of data. Okay, let's do a scatter plot. If it is on your quiz tomorrow, there will be a separate part with the graphic calculator. Yeah. Okay, so we go stat, edit, dot, 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 clear out your old list. Zero, 1, 2, 3, 4, 5, 6. And then over here, 0, 3, 5, 10, 19, 38, 70. Okay? Good. Go second stat plot. Make sure it is turned on with L1 and L2 as your X list and Y list. I'm going to go to Y equals and clear out anything I might have in there first. And then, yeah, do a zoom 9. How's that set of data look to you?
Exponential.
It looks pretty darn exponential, yeah? Okay? So I want to try and fit an exponential function to that perfectly. Agreed?
Well, as close as possible.
Well, yeah, as close as possible. Not perfectly. Is there an exponential that probably goes through all 7 of those points perfectly? No, I doubt it. So I want to find one that just fits the data as best possible, best fit. So here's what we could do. Go back to your stat menu. Now, for now, here's what I want you to do. I want you to ignore that if you go to the calc menu and scroll down a little bit, there's this thing called exponential regression. Ignore that. Pretend you didn't see that. Okay? Pretend you see nothing. Let's suppose our calculator has nothing but linear regressions, and that's it. Okay? So I'm going to go back to my table. I want to create a new set of data that has the same x-coordinates as this set of data, but the y-coordinates are just the natural log or common log, it doesn't even matter, of the y-coordinates. So I could go through and do that manually, natural log 0. Oh, that is going to create a problem, isn't it?
Yeah.
Yeah, let's change this to 1. I just don't want to have a problem. Okay? All right. Now, I could manually do natural log 1, then hit enter, natural log 3, hit enter, natural log 5, hit enter. But what you can do is go up here and highlight L3 and actually say natural log of L2, which is second 2. So then when you hit enter, it fills in all of them with their respective natural logs.
Do you care if we use natural log or log?
Don't care. Okay? So now if I go back to my stat plot, second y equals, and I change the scatter plot to use L1 and L3 instead, right? Then hit zoom 9, or zoom. Normally don't, for some reason the alpha is it. Zoom 9, there we go. Does that look linear? Yes. The more linear that is, the more exponential your original set of data was. Right? That's really darn linear, so therefore my exponential is going to be really darn exponential. So now let's fit a line to this. Let's go stat, calc, linreg. Make sure you use your linear set of data, which was L1 and what? L3. That's your transformed linear set of data. So here's the equation of a line that fits that goes through the linear set of data, L1, L3. So y equals 0.6842x plus 0.2103. So that line fits the transformed linear set of data, but not the exponential set of data, Alex.
For some reason, I got maybe the 80.
Oh, really? Well, you probably take the number in slightly.
You can, there's a way to turn the correlation off.
But there's a way to turn the correlation coefficient on and off here in your mode. But how far off are your in between?
They were far off, but I technically did that. They had the line and
well, now when I do linear, I use that. Okay, you get L1 and L3. So linreg L1 comma L3. Yeah, but why is your beat so far off? Did everybody get the same thing I got?
Yeah.
Yeah, you just had to put together. 1, 3, 5, 10, 11, 6, 8, 7, 8. Did you do common log or natural log? Oh, that's why your numbers are different.
Oh.
Yeah, you're okay. You're good. Yeah. Yours will be different if you did common log versus natural log, but you're still on the right track. Right?
I turn on the
Go to mode. I've shown this before. Cool. You have to do that one. Okay. Now, I think you should get the same correlation coefficient.
Yes.
That's interesting. Common log versus natural log gives you different A's and B's, but the same exact correlation coefficient. Makes sense, though. Right? Okay. Now, how do I take this line and convert it back to that exponential?
You have to erase it.
Right.
Or the E.
This line right here is not y equals. Listen. That line is not y equals 0.6842x plus 0.2103. It's natural log of y equals 0.6842x plus 0.2103. So we need, and if you use common log, you're going to raise both sides to the power of what? 10. I'm going to raise both sides to the power of base e. So what we really get is e to the 0.6842x plus 0.2103, right? So if I go to my y equals and I type e raised to the 0.6842x plus 0.2103, and if I change my stat plot to go back to being L1 and L2, and I do a zoom 9, So there's our exponential set of data, and look at that curve. Fit that data beautifully. Right? So make sure you set your scatter plot back to L1 and L2, and then graph that at in your y equals. Okay? So does that make sense? And whatever your correlation coefficient was for your linear regression, it's the same thing for this one. Right? If we quit, so our correlation coefficient was, whoops, that's not right. But anyway, go back to your stat menu, go to calc, and actually find the exponential regression now. Let's do an exponential regression with L1 and L2. Same exact correlation coefficient, correct? But I'm not seeing the same numbers. It's telling me that this is 1.2341 times 1.9822 to the x power. Is this equation the same as that? It is. Because what is e raised to the 0.6842 power? 1.9822. And what is e raised to the 0.2103 power? It is 1.2341. Okay? Because what technically happens here, this becomes e to the 0.6842x times e to the 0.2103. Because how do you multiply powers that have the same base? You add the exponents. So can't I use that rule backwards? If you see an addition in your exponent, can you rewrite that as a multiplication of two powers? So then e to the 0.2103 becomes this. E to the 0.6842 becomes that. And so they are the same. That's pretty cool. And the correlation coefficient was identical. So with your graphing calculator, you can just do exponential regressions. But the idea is it's really just a linear regression where you transform your data first.
Will you ever do data that will cause an overflow?
Oh, no. Is that what they do in stats? No, because realistically, if you're a statistician and you've got a set of data that makes your graphing calculator overflow, you're just going to go to a computer that can actually just do it. Yeah, you'll have some multiple of however long it takes me. I mean, let's be honest. It probably takes you the same time as you to plug numbers into that stat menu.
No.
Oh, come on. Yeah.
Big question on the table.
Yes.
On the last one, why did you keep the x up there with it?
Because there's an intermediate step I kind of skipped. I can rewrite this as e to the 0.6842 raised to the x. Because how do you raise power to a power? You multiply the exponents. So isn't this the same as if I just multiply those exponents? Great question. So then inside the parentheses, that becomes 1.9822. Very good. Yeah. Okay. Here's some real-life data from the United States Census Bureau about the world population in millions. So 6,600 million is 6.6 billion, right? So we can see the population growth. I didn't want to start with this example because when you graph the scatter plot, it looks linear. It really does. But because it's a population growth, you should know that you actually want to fit an exponential curve to it, not a line, right? So that's where you use your pre-existing science knowledge to know that populations grow logistically or exponentially. All right. So let's type this in. I might not type 1998, 2000. I might say, I don't know. What do you want to make our? You just want to go 0, 1, 2, 3, 4. So we're going to call 0 the year 19. What year did it start with? We're going to start with 0 the year 1998. So 0, 99, 2000, 2001, 2002, 2003, 4, 5, 6, 7. That's 10 data points, agreed? So we've got 59, 30, 6006, 6082, 6156, 6230, 6303, 6377, 6451, 6525, and 6600. Agreed. So if we do this scatter plot, second plot, that's clear out my graph, do a zoom 9, there we go. Looks linear, right? But we want to do an exponential regression instead, so we can get that calc, exponential regression, L1, L2, bada bing. Look at that. The correlation coefficient was 0.9998. That's insane. It's almost a perfect fit. Just for funsies, let's do a linear regression. Because it looked linear, didn't it? Oh, okay, so to be honest, the line fits the data better than an exponential. Okay, it doesn't mean the data was exponential. This is a very, very small sampling of world population growth. This is 10 years out of how many? Lots. Okay? Lots and lots and lots. So that does not mean you decide to use a line to represent this data. That is not what that means at all. Okay? Realistically, though, is the population going to continue growing according to whatever exponential curve we get? Yeah, at some point it's got to, right?
When we keep moving, you'll carry by technology.
Right. So let's go back to our exponential regression. Let's see what that looks like. Okay, so there's the equation. 5,937 times 1 point. Look at that. 1.001. That base is really, really close to being 1. So it's not nearly the exponential growth that like a bacteria population would grow with, right? It's pretty slow growing exponential. What is exponential? Why? Didn't this mess? You might have 10 numbers typed into your exploits, maybe you'll do 9. Why? Go back to 6,000. Okay, let's predict, when is this population going to hit 7 billion people? So I need to take 5,937.1293 or 129 times 1.0119 to the x power and set that equal to what? 7,000, because the number 7,000 represents 7 billion people, right? So then how do you solve that equation? Divide. So you have 7,000 divided by 5,937.129. Then we do what to both sides? Take a log, pick whatever log you want. I pick natural log. Bring the x down. So you have x, natural log 1.0119, equals the natural log of 7,000 over 5,937.129, and then divide. So you're going to have x equals natural log 7,000 over 5,937.129, all divided by the natural log of 1.0119. Right? Is that nice? Let's type that in. The natural log of 7,000 divided by 5,937.129, close parentheses, divided by natural log 1.0119, that gives me 13. Now, 0 was what year? 1998. So, in the year 2011, 0.9. So if I multiply that by 365, it's whatever the 336th day of 2011 was. What did I say, 336?
Yeah.
Google will fix it. What?
You're probably right, 2011.
Isn't the 336th day of any year going to be the same?
Yeah.
Except for leap years?
Yeah.
What is the 336th day of the year? What is it? December 2nd? You see that? Here we go. 336 is December 2nd, yep. Now, let's see if we can find a news article.
Oh my God. I'm pretty sure the National Geographic for like December or November of last year said 6-7
October 30th was when the USA Today published an article. October 30th. That's interesting, because I remember doing this lesson last year. I wonder if I made a mistake typing something in. Because I remember doing this lesson last year, and it was around this time of the year, or actually a little bit later in the year. And whatever date we had predicted hit 7 billion was literally like 2 days from what day I was teaching it. And sure enough, like, that article did. It was like October 28th when we did this problem. And we came up with October 30th. Or something weird like that. I can't remember. Or we were doing the lesson now, but we predicted October 28th as the date. And October 30th is when the article was published. It was pretty awesome. That's all I got.